All right, so now that we've seen the Riemann sum definition of what a double integral looks like, let's learn how to actually compute this. And it's really not so bad over a rectangle, and I think you'll find it's not so bad in general either, but let's get the rectangle out of the way first, since that's the easy case. All right, so you'll notice here I rewrote the double integral as its Riemann sum, but in two different ways. In this one, I wrote it where you do the limit for the n's first, the j limit for, or yeah, n goes to infinity. So that's for the y direction. That happens first. You'll also note I rewrote delta a as delta x delta y, or delta y delta x in this case, and I've put the parentheses in a very suggestive way. All right, so if we look at this side, does this inside here look familiar to you by any chance? Hopefully it does, because you should just see limit as m goes to infinity, the sum from I equals 1 to m. But what is this on the inside here? Well, it's just the Riemann sum for an integral in one variable, and it happens to be the y variable here. So really this is integral from c to d of f of xi, comma y, dy. Then we have delta x out here. Okay? Actually, let's put the equal sign on the other side to match it up with up here. All right? Let's put one here too, why not? Okay. So does that make sense? Hopefully it does. And now we're going to do it again, but for x now. Because now this thing on the inside is just the only kind of variable thing around is the xi's. So now we do this again, and we end up with an integral from a to b of this integral from c to d of f of xy dy, then dx. All right? So that's sort of how this works. If we do it this way, we integrate the y variable first, pretending x is a constant. Remember, that's exactly how partial derivatives worked. Right? And then we integrate the x variable, because that's the only thing that's left. There are no, once you've done this integral on the inside, there's no more y's left. Okay? Like, think of when you do a definite integral with one variable, the thing you get at the end is a number. Okay? Now if we go over here, we can do pretty much the same thing. All right? So limit as n goes to infinity, sum j equals 1 to n. This inside, now we're doing the Riemann sum for the x variable first. So this is just a to b f of x y sub j dx parentheses delta y. And then this converts to integral from c to d of integral from a to b f of x y dx parentheses dy. Right? So we get that these two things are the same as this. Right? So these are the two ways we can compute a double integral over a rectangle. We can do the y's first, then the x, or we can do the x's first, then the y. All right, I do want to point out that for a rectangle, it's fine to just kind of flip the integrals like this, and do whichever order you want. But in general, it's a little bit trickier than just flipping the bounds. All right, we'll see that in a couple videos. But what I want to say is the fact that these two are equal is something called Fubini's theorem. So equality here this is Fubini's theorem. Right? Just want to point that out for you. Okay, so now let's just do a quick example of computing a double integral. All right, so let's see an example of computing a double integral. And it's pretty straightforward, so let's just get right into it. All right, so we want to compute the integral from 0 to pi over 2, 0 to 1, of y cosine x dy dx. All right, So the important thing to remember here when you're doing multiple integrals is we always work from the inside out. Right? So this thing inside the green parentheses here always happens, you always do this one first, then the outside one. Okay, think back to the Riemann sums. We had the parentheses in the middle. Okay, so this guy always has to happen first. So let's go ahead and do that. Integral from 0 to pi over 2. So if we're going to integrate y cosine x with respect to y, all right, remember x, just like in partial derivatives, is pretty much a constant as far as y cares. So when we integrate it, we just treat all of cosine x as just a constant and integrate with respect to y. So that gives us 1/2 y squared cosine x, right? And this is from 0 to 1 dx. Okay, hopefully that makes sense. And then now we got to evaluate the inside for those limits. So we have 0 to pi over 2. Plug in 1 for y squared, and we're just left with 1/2 cosine x. Plug in the 0, and we just get 0. So we can just leave it off. Or let's put the -0 here, just for the video. Right? You can leave it off later. All right? And now we have to integrate this with respect to x. Well, so let's just rewrite that. 0 to pi over 2 of 1/2 cosine x dx. Right? So we have to integrate this with respect to x, but this is just back to Calc 1. Right? So this becomes 1/2 integral of cosine is sine x from 0 to pi over 2. Right? So now just plug in these two things. 1/2 sine of pi over 2. Well, sine of pi over 2 is 1, so that's just 1/2. Plug in 0. Sine of 0 is 0, so that's it. Right? So our answer is just 1/2. Right? So now try on your own taking these two integrals, flipping them, and of course you've got to flip these two. So in other words, try on your own computing the integral 0 to 1, 0 to pi over 2 of y cosine x dx dy, and see what you end up with. All right? If you watched the previous video where I mentioned the Fubini theorem, you should hopefully get 1/2. All right? See you in the next one.